In this video, we will talk about the second derivative test. So this is going to be another way for us to classify whether our critical numbers are local maxes or local mins, and it says the following. So if C is a critical number of f, and if the second derivative of f evaluated at C is greater than 0, so if it's positive, then f has a... So before I say what f has, I'm going to motivate this with a picture. So I'm going to draw some axes. Okay, so C is a critical number, and we're saying that the second derivative at C is greater than 0. So we're talking about a graph that's going to be concave up. Okay, so at that critical number, so the critical number here, I'm going to label this as C. Our graph is concave up. And we can see by looking at the picture that at that critical number, we have a local min. So f has a local min at C. Okay, so that's the first case. The second case is if our second derivative evaluated at C is less than 0. If it's negative, then our function f has a, and again, I'm going to draw a picture to motivate it. So this time our second derivative is less than 0, so we need a function that is concave down. Okay, and if I label this critical number as C, this place where my graph gets flat, so I can see that my graph is now concave down. So at that critical number, we have a local max. F has a local max at C. Okay, and the third and final situation is, what if the second derivative at C either equals 0 or is undefined? So those are the only other possibilities. So if those happen, this test, this is called the second derivative test, this test is inconclusive. Inconclusive, which means it doesn't give us any information. So if the test is inconclusive, then we'd have to go back and use the first derivative test. So remember, the first derivative test is that thing where I make a number line and see where's the first derivative positive, where's the first derivative negative, so I can see where's my function increasing and where's it decreasing. Okay, so why is the second derivative test, why is it inconclusive? Why do I get no information when I plug in my critical number and it either equals 0 or is undefined? So I want to look at two examples where that happens to show you that different things can happen. Okay, so if I look at the function f of x and I call this, I just call it f of x, and my function is x to the third, the derivative of this, let's find critical numbers. The derivative of this is 3x squared. And this which has a critical number at, so this is never going to be undefined, but it can be equal to 0, and it will be equal to 0 when x equals 0. Okay, so now let's try plugging that into the second derivative. So, but when we do the second derivative is 6x. So now this implies when I plug 0 into it, we get 6 times 0. So times 0, which is 0. Okay, so let's look at the graph of this function to see, well, what actually is going on at this critical number. So y equals x cubed. This is a function that we know the graph of. If we weren't sure, we could just plot some points in this quickly to get a feel for the graph. But the graph of x cubed, this sort of snakes upwards like this, gets really, really flat. It's perfectly flat here, and then it keeps going up. And I know it gets perfectly flat there when x is 0, because that's a critical number. The derivative equals 0, meaning the slope of the tangent line is 0 at that point. And if I look at this picture, at this critical number, well, this is neither. It's not a local max, nor a local min. Neither a max, nor a min. So what this shows is, sometimes when our second derivative equals 0 at our critical number, we could have a situation where the critical number is neither a max nor a min. But that doesn't always happen. Sometimes it could be a max or a min. So I want to show you one other example. Okay, and this will demonstrate that it really is inconclusive. So if I look at the function g of x, and I say this is x to the fourth, let's do the same thing. Its derivative is 4x to the third, and this has a critical number at, it'll never be undefined because there's no fraction here. I don't have to worry about the denominator being 0. But this can be equal to 0 at x equals 0. Okay, so I have this critical number. Now let's take the second derivative. But I'm going to notice that when I take the second derivative, which is 12x squared, now let's plug in that critical number. Let's plug 0 into this. And I'll get 12 times 0 squared, which is just 0. Okay, and if I look at the graph of this function, so y equals x to the fourth, this function's graph kind of looks like a parabola almost. Looks very, very similar. It's just a lot narrower, it turns out. Okay, but if I look at this picture, at this critical number, we have a local min. So what these two examples show is that when we have a critical number, and I test it using the second derivative, and I plug it in to the second derivative, and it equals 0, I could have a situation where it's not a local max or a local min, like I did with x cubed. I could have a situation like x to the fourth, where I end up with a local min. I could also come up with a situation easily where I end up with a local max. That's why it's inconclusive. From knowing that the second derivative is 0, or it's undefined, this gives me no information. Okay, so let's do an example. All right, so this is a function that we've been looking at over a few videos in this section, x to the 5 over 5 minus 8/3 x cubed plus 2. And we're going to now do part E of this example. We want to use the second derivative test to classify the critical numbers. So recall that the critical numbers, we had found these already, and these are x equals negative root 8, 0, and positive root 8. And our second derivative, it's actually going to be nicest to use the factored form of it, and we had gotten that earlier. This was 4x times x minus 2 times x plus 2. So we had shown this in a previous video. So now let's plug in our critical numbers into that second derivative. So let's first do the second derivative evaluated at negative root 8. If we plug that in, we get 4 times negative root 8 times negative root 8 minus 2 times negative root 8 plus 2. And because it's factored, I just need to determine if each of these things is positive or negative. Okay, so the 4 is definitely a positive number. The negative root 8 is definitely negative. Negative root 8 minus 2, that is definitely negative. For the negative root 8 plus 2, this one might be a little bit trickier, but it turns out it is negative because negative root 8. So root 8 is bigger than root 4, and root 4 is 2. So that means negative root 8 is going to be less than negative 2. So even when you add 2 to it, it'll still be a negative number. Okay, so overall, a positive times 3 negatives, that is going to be a negative number. So that means when my second derivative is negative, it means I have a concave down situation. And then at my critical number, we have a max. We have a local max at x equals negative root 8. Okay, let's test our other critical numbers. All right, so let's do the second derivative now evaluated at positive root 8. We'll get 4 times positive root 8 times positive root 8 minus 2 times positive root 8 plus 2. If we do the same type of sign analysis, 4 is a positive number, root 8 is positive. Root 8 minus 2, this is going to be positive because we already saw that root 8 is bigger than 2. And then root 8 plus 2 is definitely positive. So 4 positives multiplied is definitely positive. Now my second derivative is positive, so we have a concave up picture. So at my critical number, we are going to have a local min. So we will have a local min. Local min at x equals, this was positive root 8. Okay, so we have one final critical number to check. That was 0. So if I plug 0 into my second derivative, we'll get 4 times 0 times 0 minus 2 times 0 plus 2. Okay, and I notice that one of these factors is 0, so this whole thing is just going to multiply to 0. Okay, so this is a situation where the second derivative test is inconclusive. Second derivative test is inconclusive. It gives me no information. This does not necessarily mean that it's not a local max or a local min. It could be. It doesn't have to be neither. It just tells me that this gives me no information. And when this is inconclusive, we would use the first derivative test. And that we had done in an earlier video. So I want to end this video by giving a summary of the first and second derivative tests. So the main thing that I want to point out about the first derivative test is this always works. There isn't a situation where this will give me something inconclusive. It's always going to work. But sometimes it's longer because I have to do my whole sign analysis thing, and sometimes that can be longer. Like in this problem, it was pretty quick to just plug in numbers into the second derivative. And if I hadn't had something that was inconclusive, like this critical number 0, it would have been faster. It would have been more efficient. The second derivative test, this doesn't always work, but it can be quicker when it does work. If it's easy to find the second derivative, it can be quicker when it does work. So in terms of our goals for this section, we finished our last goal, applying the second derivative test to find local extreme points. I will do one more video in this section to give another increasing-decreasing concavity example.